In this example, we will determine the convergence or divergence of the series 3 to the k over k to the k using the ratio test. So as always, we'll start by calculating the limit of absolute value of ak plus 1 over ak as k goes to infinity. Again, the absolute value doesn't matter here because everything is positive. So ak plus 1 over ak will be 3 to the k plus 1 over k plus 1 to the k plus 1. That's the series with the terms with the k's replaced by k plus 1s, divided by ak, which is just 3 to the k times k to the k. We'll simplify by multiplying by the reciprocal of the denominator. 3 to the k plus 1 over k plus 1 to the k plus 1 multiplied by k to the k over 3 to the k. Along this diagonal I have k plus 1 threes and I have k threes. So all but 1 3 cancels and the remaining 3 is in the numerator since that's where I have more of them. So we'll write that as 3, that's k to the k, and in the denominator I'm going to write this as a k plus 1 and then a k plus 1 to the k because this is, we'll put parentheses here, because this then makes a total of k plus 1 k plus 1s. And so this is going to allow us to calculate the limit as necessary in an easier fashion. Okay, so what we're going to do, let me erase what we don't need here. Our goal is to find the limit as k goes to infinity of that mess. So we want the limit as k goes to infinity of 3 over k plus 1, I'm going to think about these things separately, times k to the k over k plus 1 to the k. That's our goal. Now, remember, I can split a limit of a product into a product of the limits as long as both things are finite. What we're going to do is we're going to take the limit of this thing and the limit of this thing separately. We'll discover that they're both finite, and so that means that we can actually just multiply them together to get the final result. That doesn't work if either of the limits are infinite. 0 times infinity or 2 times infinity, or the weird things can happen when we have infinity, so you have to be very careful about that. But if they're both finite, then we can just multiply the results. So this, let's calculate each of those limits separately, and then we'll be able to say that we can multiply them to get our result. Limit as k goes to infinity of 3 over k plus 1, that one's easy, right? As k goes to infinity, that's just 0, because the denominator goes to infinity. The other one's a little bit harder, right? So the limit as k goes to infinity of k to the k, now I'm going to write this as k over k plus 1 all raised to the k. I can do that because k is the same exponent on both. And we have to apply our logarithmic limit just like we did from some previous stuff. And so let's do that. So we're going to take the limit of the log, the limit as k goes to infinity, of the natural log of this stuff, so that I can bring that k down front. So that is the limit as k goes to infinity of k ln k over k plus 1. Now when we plug infinity in, I get infinity, and this is ln of infinity over infinity. These are both, but the limit of this inside is 1, because it's like k over k plus 1. In the end, that goes to 1. So this is 0, this is ln of 1. Sorry, this is infinity, this is ln of 1. ln of 1 is 0, so I have a 0 times, of infinity times 0. And we need to rewrite that and then use L'Hopital's rule. So after rewriting, this becomes the limit as k goes to infinity of ln of k over k plus 1 over 1 over k. So we're going to transfer the 1 over k to the denominator, so that now this is, when I plug infinity in, the inside here becomes 1. ln of 1 is 0, so this is 0 over 0 and we can apply L'Hopital's rule by taking the derivative of the top and the derivative of the bottom separately. The derivative of the top, derivative of ln is 1 over, so 1 over a fraction is the flip of the fraction, so that's k plus 1 over k, times the derivative of what's inside. We have to apply the quotient rule. The quotient rule for this is the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom. The derivative of the bottom is also 1. Minus the top times the derivative of the bottom. The derivative of the bottom is also 1, all over the bottom squared. So that will be k plus 1 squared. That's just the derivative of the numerator over here. We also have to divide by the derivative of 1 over k, which is that's k to the minus 1, so the derivative is negative k to the minus 2, which is negative 1 over k squared. We're still taking the limit as k goes to infinity. Let's ask what simplifies. This is k minus k, so that goes away. I can take a k plus 1 off with a k plus 1 down here. So this leaves me with a k cancels, so I get 1 over k times k plus 1 over negative 1 over k squared. But let's put that up top by multiplying by the reciprocal, so that's times negative k squared over 1. Now what happens when I take the limit as k goes to infinity? The numerator is negative k squared, the denominator is k squared. At least the largest degree. If you put that in, it's k squared plus k, but in the limit I only care about the k squared term, so this limit is actually negative 1. Remember that we took a natural log at the beginning of our limit, so that since, and to undo the natural log, we use the inverse exponential. That tells me that the limit of the actual beginning, this limit that we were looking at right here, is e to the negative 1. Right, we take e to what we want, e to the limit, to get our final value because we took the natural log and we have to undo that. So this limit is e to the negative 1. So that means that of the two pieces that we were starting with, the limit of 3 over k plus 1 is 0. The limit of k to the k over k plus 1 to the k is 1 over e. Since both those limits are finite values, the limit of the product of the two is actually 0. Since the limit is less than 1, that means that the original series converges.